Hello everyone, my name is Yuanjie Gong, and today I'm going to talk about one of the most pivotal disasters in European history, the 1755 Lisbon tsunami. This wasn't just a natural catastrophe, it was a cultural and scientific turning point. My presentation is titled The 1755 Lisbon Tsunami, a multidisciplinary catastrophe, and we will explore this topic through three key angles. First, the triggers and the devastation. How the earthquake, tsunami, and fires unfolded as a compound disaster. And the second is the scientific insights, what the event taught us about wave dynamics, coastal amplification, and hazard modeling. And the third one is the legacy, how it reshaped in enlightenment thought, influenced urban planning, and laid the foundation of modern disaster preparedness. And let's begin by settle the scene of what happened on that fateful day. So on the morning of November the 1st of 1755, All Saints' Day, while churches were full of worshippers and a massive offshore earthquake struck the Atlantic Ocean near Lisbon. It had a magnitude estimated between 8.5 and 9.0, and it unleashed a chain of disaster. The quake itself leveled much of the city, then a powerful tsunami swept in, followed by fires that burned for days. The scale was apocalyptic. Between 60,000 and 100,000 people lost their lives. And beyond this physical devastation, the event shocked the Europeans' worldview. It forced people to ask, was this the divine punishment, or could natural be explained through science? So let's take a moment to visualize the scope of the disaster. What you're looking at here is a tsunami propagation map created by NOAA and the Pacific Tsunami Warning Center. It shows the Atlantic Ocean basin and how the 1755 tsunami radiated outward after the earthquake. The red star here marks the earthquake's epicenter, which occurred just offshore, and what we now call the Azore-Gibraltar fault zone. It was this powerful underwater rip rupture that generated the waves. Over here, you will see the Lesbian is here, right on the western coast of Portugal. What's important to notice is the shape of Lisbon Bay. It's narrow and funnel-like, and that may seem worse. As the waves traveled inward, the bay focused their energy, increased their height and destructive power. Some eyewitnesses described the sea vanished before a massive wall of water came in crashing in. It wasn't just one wave, there were multiple surges, amplified by the bay's shape. And this wasn't just a regional event. Look at how far the energy traveled. Waves reached the Caribbean and eastern coast of South America, and even in British Aires. Imagine experiencing an earthquake in Portugal and within hours, feeling its effects across the Atlantic, and that's the scale we are dealing with. So far, we've seen where and when the Lisbon disaster happened, but now it's time to dig into how it unfolded. The shaking itself was felt as far as North America and Scandinavia, but the real devastation came in waves. Literally, what made this event so unique wasn't just the earthquake, it was the chain disaster that followed. First came the violent shaking, then the tsunami waves, and finally the fire that rages through what was left of the city. Let's begin the first trigger, the earthquake itself. Let's look at how this all began. On the morning of November the 1st, a powerful earthquake struck just off the coast of Portugal. This was like a strike-slip event. What tectonic plates slide past each other horizontally, while what type of movement doesn't usually generate large tsunamis. In this case, the rupture caused a sudden vertical displacement of the seafloor, and that movement displaced massive volumes of water, and that's what triggered the tsunami. According to historical reports and modern models, the waves reached up to 5 meters in Lisbon, but were even more extreme, as high as 20 meters on the coast of Morocco. And this wasn't a local wave, it crossed the Atlantic. And we'll come back to the transatlantic impact in a moment. But first, let's look at what this meant for the people of Lisbon. The Lisbon earthquake wasn't just one disaster, it was a sequence of catastrophes. And after the quake, towering tsunami waves swept through the city's harbor, destroying everything in their path. One survivor wrote, "The sea vanished, then returned as a wall of black water. As, as if that weren't enough, the tsunami sparked fires throughout the cities. Candles, overturned stoves, and collapsed buildings ignited widespread flames that burned for days. In total, around 85% of Lisbon was destroyed, and between 6,000 and 100,000 people were killed. To put that in perspective, Japan's devastation 2011 tsunami caused about 18,000 deaths. Lisbon's toll was far higher, especially given the population and the lack of warning systems. It was one of the deadliest and most complex disasters in European history. So how did the 1755 tsunami travel so fast? And why it's so devastating when it reached Lisbon? Let's start with the science behind wave speed. In deep ocean water, we can use a simple formula to estimate tsunami velocity. V equals to the root of g times d, where g is the gravity and d is the water depth. With an ocean depth of around 4,000 meters, and that gives us a speed of nearly 700 kilometers per hour, comparable to a passenger jet. As you can see in this diagram on the left, tsunami waves move quickly in depth water, but they're actually barely noticeable at sea, only a few centimeters tall. But when they reach the coastal line, things change dramatically. The waves slow down, and as their speed decreases, their height increases. This is where the destructive really begins. But Lisbon had a particularly vulnerability. It's funnel shaped. In the diagram on the right, you can see what happens when waves enter a narrow coastal line. Wave energy gets concentrated, and the wave height increases even more. This process, called coastal resonance, means that Lisbon wasn't just hit, it was amplified. A tsunami that might have been survivable elsewhere became catastrophic because of the city geography. What you're looking at here is a computer simulation of the 1755 Lisbon tsunami. This model shows how the waves move through the Lisbon coastal line over time, from 30 to 120 minutes after the earthquake. Red areas indicate higher water levels, and blue areas show where the sea was pulled back. Scientists today use simulators like this to reconstruct historical tsunamis, based on physics, seafloor topography, and historical accounts. But even with modern tools, there are still big uncertainties. We don't know exactly what kind of fault movement occurred. Was it purely a strike slip, or did it involve uplift, and we have no detailed records of the seafloor shape or bathymetry from 1755. These variables can dramatically change the model results. So even today, scientists are still debating the exact mechanisms behind the Lisbon tsunami. They say this event did something remarkable. It sparked the use of damaged reserves, eyewitness reports, and physical evidence to better understand earthquakes. In a way, the science of seismology was born from this disaster, and what began with damage reports and uncertainty would eventually become the foundation of modern ocean forecasting systems. But Lisbon's impact did not stop at seismology. It also sparked some of the first serious scientific questions about ocean itself. When the tsunami struck Lisbon in 1755, it didn't just destroy a city, it opened the door to some of the first real questions in ocean science. Suddenly, scholars weren't asking, why did this happen in a religious science sense? They were asking, how fast did the waves travel? And why did some places get hit harder than others? And what role did the shape of the seafloor play? For wave speeds, reports from ships and coastal communities, especially from as far as the Caribbean, suggested that the waves across the Atlantic at hundreds of kilometers per hour. That was the beginning of shallow water wave theory. But speed was only part of the puzzle. Look at the simulation. The wave energy isn't moving in a perfect circle. Instead, it reflects, refracts, and sometimes interferes with itself, all due to seafloor structure. And that's what we now call propagation effects. In some regions, waves are amplified by the terrain, and in others, they cancel out. The Lisbon tsunami revealed that ocean dynamics are deeply tied to underwater topography. And while no one in 1755 had satellites or sensors, the questions they started asking are the same ones oceanography is still working today. The Lisbon tsunami hit without warning. People saw the ocean disappear, and then it came back as a wall of water. But today things are different. We now have a global network of real-time tsunami detection systems, and at the heart of it is something called DART, short for Deep Ocean Assessment and Reporting of Tsunamis. And here's how it works. A tsunami sits on the seafloor, sometimes 4,000 or even 6,000 meters deep. It constantly measures water pressure when a tsunami wave passes by, even if it's just a few centimeters tall out in the deep ocean. That pressure changes slightly. The signal is sent acoustically via sound waves up to a surface bouncy floating on the ocean. The buoy then transmits the data instantly via satellites to global tsunami warning centers. These systems are now deployed all around the world, in the Pacific, the Atlantic, and the Indian Ocean. And the difference is real. Thanks to systems like DART, many coastal regions now have minutes or even hours of warning before a tsunami arrives. But Lisbon had none of this. No sensors, no warnings, no chance to prepare. And that's what we've built since 1755. It isn't just technology. It's a direct response to the history we never want to repeat. So here's the bigger picture. And this isn't just a map, it's the global tsunami warning system in action. Every triangle you see marks a country or region with a capability to detect, monitor, and respond to tsunami threats. This is the kind of international system we've built since Lisbon. And the fact that it even includes the North Atlantic and the Mediterranean, where Lisbon sits, really shows how far we've come. These systems rely on a combination of dart-borne seafloor pressure sensors, satellites, and emergency protocols. All work together in real time. If an earthquake strikes near the ocean today, sensors pick it up within minutes. Models simulate the waves path, and alerts go out, sometimes before the first wave even reaches shore. Back in 1755, none of this exists. The wave just came. And now the ocean is under constantly watch, 24/7 globally. And that global awareness, that readiness, is the legacy that Lisbon helped us to create. So what did the 1755 Lisbon tsunami really change? It did not just break buildings, it broke assumptions. People stopped asking only why did this happen and start asking how can we understand it? How can we prepare for the next one? And that shift from fear to science, from disaster to design, was the true legacy of Lisbon. It gave rise to early tsunami studies, pushed governments to rethink urban planning, and laid the foundation for the science we now rely on today. In a way, the 1755 tsunami helped invent modern risk thinking and showed us that resilience begins not after the wave, but long before it hits. And it's that mindset of preparation of reaction that we carry forward today.